All right. Welcome back. This is Academia SC. Um, yes. So we'll be dealing with another topic today. It's a cool topic. Um, it's called titration, right? Now we spoke about the reactions, types of reactions with regards to acids and bases, and we spoke about the pH of an acid, pH of a base, and we know that the pH of an acid is in between 0 and 6. Then the pH of a base is between 8 and 14, right? And we know that 7 is a neutral state. Right. Now we are in a segment where we gonna talk about titration. What could titration be? Now titration is when we add a base or an acid in a substance. It can either be base or it can either be an acid, right? If we take a base, we'll have to add it to an acid. The sole purpose of doing that is to neutralize that substance, right? So when we say neutralize, we mean that that's neutralization, right? The process of what? Transforming your base, a strong base or your base, into a neutral substance where the pH is going to be what? 7, right? Now that's neutralization. So we have to add, if we have a strong base, we add let's say we add a weak acid. Then when we add a weak acid, the sole purpose of doing that is to neutralize the substance or to neutralize the reaction, right? Now let me give you an example. Let's say we have the sodium hydroxide, right? Sodium hydroxide, and we add it to hydrochloric acid. Now if we look at this, this will give us or will give rise to what we call the sodium chloride and water, right? H2. Oh, this is a liquid, right? This is a solid. This is in aqueous form, and this is in aqueous form, right? Now basically that's just what we have. So ours, we look at this thing, right? If we take your sodium ion and we add water to it, right? And we add water to it, right? This will not hydrolyze, right? What do we mean by hydrolysis? The breaking down, meaning that the water molecule won't be able to dissolve the system or the substance, right? Because this is going to be your solid, right? Now with chlorine, this is also a solid. So being a solid, if we add water like that, right? If we add the water like that, there will be no hydrolysis on this, right? There will be no hydrolysis on this, meaning that the substance won't break, right? Now this normally happens, right, if you have a strong acid that reacts with a strong base, right? Now let's look at a strong acid plus a weak base. Normally if you have a strong acid and a weak base, the pH will still be less than 7, right? Now why is it like that? Remember, this is a strong acid, right? Strong acid plus weak base, right? Obviously the weak base, in terms of if we use the oxidation reduction form, then we'll know that this will serve as the oxidizing agent and this will be the, this will be the reducing agent, this will be the oxidizing agent, right? Now, that's basically that. We look at it in that form, right? It's more like saying 5 plus minus 1, right? Obviously, you're still gonna have a 4, which is greater than negative 1. And in this form here, when we were speaking of this, you're going to have what? 4 minus 4, right? Which is 0. The neutralization is there, right? Now, with substances such as or rather with reactions such as the hydrochloric acid, the strong acid plus a weak base, let's say NH4, NH3, the ammonium, right? The hydrochloric acid plus the ammonium, right? Obviously, this will give rise to NH4, which is ammonia, plus what? Chlorine, right? Now, that is the case. Now, this is supposed to be 4. Right, that is the case with the reactions, right? This chlorine will be negative. Now, listen, and listen very carefully. If you have a substance like this, right? If you have a substance like this is a strong acid, this is strong, and this is weak. Now, this and this will give you the results, right? Remember, this is an acid, this is a base. Now this will be the acid and this will be the what? This will be the base, this will be the acid, sorry. This will be the base, this will be the acid, right? Now, listen, if we were to hydrate these substances here, NH4 plus water, we hydrate it, we add water to it. This was going to give us NH3 plus H3O, which is the hydronium ion, right? It was going to give us the hydronium ion. Now with chlorine, remember, chlorine does not hydrolyze, right? Meaning that there won't be any hydrolysis to this. Exactly. Now let's check this example here. That's what this is basically what we're going to be talking about, and also the calculations. We are most familiar with them, right? But we're just gonna get deep into them, right? Now you have acetic acid, which is a weak base, right? Now this is condition number 3. This is condition number 1, right? Where is it? This is condition number 1. This is condition number 2, and this is condition number 3. If we add a weak acid and a strong base, the pH is going to be greater than 7. It's more like saying if we had 2 plus minus 7, right? Obviously this will lead into what? This will lead into negative 3. Is it negative 3 or negative 5? Sorry, it's gonna lead to negative 5, right? Now, being a negative, we still have a base. It is still basic, right? It still is a base. It's just that it just dropped by 2 points, right? Now, I'm just using these mathematical expressions as an example. They are too abstract. They are not precise, right? Now, let's say we add the acetic acid. This is the weakest acid that we know of, right? The acetic acid and the sodium hydroxide, right? The sodium hydroxide. Now, the hydroxide is going to be it's going to be a strong base, right? Now, note that the sodium ions will not hydrolyze. Obviously, we have spoken about that. Now, but the acetic ions hydrates to form the hydroxides, right? Ions, right? Now the pH should be greater than 7. That's the case, right? Let's say let me give you this. This is Na, right? Plus the sodium plus water, which is H2O. This we said there's no hydrolysis. Then if we have the acetic acid like this, CH3 double O negative, right? Plus water, then what we get is we get the CH3, right? OOH plus the OH. This is the hydroxide. Now remember, this is a it's a carboxylic acid, right? It means we're going to have, if you have your acetic acid and your water, you have your carboxylic acid and your hydroxide. Now that's what we need to be familiar with. Now I have steps that I want us we deal with or we look at. These are the steps to follow when you're doing titration. Now step number 1 is you have to accurately weigh the correct amount of solid, right, in a watch glass on a balance, right? The solid has to be measured or weighed accordingly. The solid has to be properly weighed. Now number 2, transfer the solid to a volumetric flask through a funnel, right? Now because there is a solution, now we have weighed the matter and we put it in the glass. Obviously we can transfer the solid into a volumetric flask through a funnel. Use this, right? Now add a small amount of water and whatnot. Now this is the example, or this as the steps when you are doing the actual experiment, right? So now let's go to titration calculations. Now these are, to some it's gonna seem difficult, but I'm just gonna try to explain them into simple form. Titration calculations, we use neutralization titrations to determine the unknown concentration of an acid or a base, the equivalence point, the number of moles of a hydrogen ion equals the number of the moles of a hydroxide, right? We know that the number of moles is equals to concentration times the volume, right? Now this should be small letter, something like this, right? N equals to CV, curriculum vitae. So now applying the equation, what are we going to say? If we have the mole of an acid, then the concentration of an acid and the volume of an acid, divide this by the number of mole of a base, divide this by the concentration of a base, then the volume of a base, something like that, right? Now that's basically what we need to be familiar with, right? Number of moles of an acid, concentration of an acid, volume of an acid, number of moles of a base, concentration of a base, then volume of a base. Now that is basically what we need to be familiar. This is the first formula that we need to know. So now how do we use this? Let's say you are given this example here and they say to you, in a titration you have the what, 30 centimeter cubed, right, of sulfuric acid, right, of sulfuric acid. Now then they say which is neutralized by exactly 40.0 cm3 centimeter cubed, right, of what, potassium hydroxide, potassium hydroxide, hydroxide, right? Now we need to consider, we have, this is going to be your base, right? This is going to be your base and this is going to be your acid. Now what are they saying? That the potassium hydroxide solution of a concentration is what? The concentration of the base or the potassium hydroxide is 0.200 dm mole per dm, right? Mole per dm, decameter cubed. Right. Let's see, mole per dm, right? Not necessarily, yes. Now what are they saying? Calculate the concentration of the sulfuric acid, right? We have, okay, for this one we have the volume, right? For this one we have the concentration and the volume, right? Now listen, there is something that is hidden in this statement, right? Now, which is something that you need to do. You need to say we have the sulfuric acid, H2SO4, right, plus the potassium hydroxide. Then it takes us to the potassium sulfate. Sorry, it should be K. Potassium sulfate, K2SO4, also plus what? Water, H2O. Now with this solution you will need to first balance the equation, right? Now if we look at this, here you have 2 hydrogen, there you have 2 hydrogen, here you have 1 hydrogen, you have oxygen, you have oxygen, and this here is going to be 5, right? Now 4 plus 1 is 5, 4 plus 1 is 5, then here you have another hydrogen, which means it's 3, right? Now we need to solve this. What can we do in order to solve this, or to balance this equation, right? Now to balance this equation we're going to try something. Let's think about it. If you have H2, right, this is going to be 1 plus 1, which is 3, right? This side is going to be 2, right? Basically if I added 2 here and I add another 2 here, I should get a balanced solution, right? Now let's verify this. To verify this, what are we going to do? We're going to multiply 2 by K, which is going to be K2, right? Then we're going to multiply oxygen by 2, which is 2. Then we have 2 plus 4, which is going to be what? 6, right? Now 2 by hydrogen, this is going to be 4, right? This side, distribute 2 here, you're going to have H, it's going to be 4 hydrogens. Then on that side we're going to have 2. 2 plus 4 is going to be 4. Basically it's balanced. So now that it's balanced, what can we do? What we need to do is to focus on the number of moles of these. Remember, this is the acid and this is the base, right? So now this represents the number of mole. The coefficient here represents the number of mole. So we will conclude by saying what? Na is equal to 1. So with this base here, Nb, let me rewrite this, it's what? NB, that will be equal to 2, right? That is that. So now we have everything. We have the number of moles of acid, a number of moles of base. Then we have the concentration of the base, the concentration of not the concentration, but the volumes of both the base and the acid. So what do? We say Na over Nb equals to CV. This is A, and this is CB, VB, something like this. So now we have the formulas. We have this is 1 over 2, then which is equal to this one here is going to be Ca, because we want the concentration. Then what is the volume there? If we look at the volume is 30, right? Then you multiply by 30 divided by what is the concentration of the base. The concentration of the base is 0 0.20. Then here you have what? You have your volume, which is going to be what? 40. The volume of the base is 40. So now we need to find the concentration of this. When solving this, we cross multiply. You have 2 into 30 Ca, which is equals to, then you have 0 0.200 multiplied by 40 multiplied by 1, right? Divided by 60. 2 by 30 is 60. Then Ca is going to be what? 0 0.20 multiplied by 40, right? By 40, then divided by 60. Solving this, how much do we have? We're going to end up having 0 0.133 mole per decameter cubed. That is basically how you can solve this, right? So we're not gonna dwell much on it. Let's go to the ionization of water, right? If you don't understand something, you'll go back and check this. Then I'll try to post up some things on the video so that you can be able to do some activities, right? So let's go to ionization of water. Let's write H2O and Kw. So now water undergoes self-ionization. Water does not need any substance to ionize itself, right? So what can we say about this? This is going to be easy to understand only and only if you pay attention, right? Water undergoes self-ionization, right? When a water molecule loses the hydrogen ion to form the hydroxide. A hydrogen ion is the nucleus of the one of the hydrogen atoms, right? So now the hydrogen nucleus immediately protonates. It accumulates a proton. It protonates another water molecule to form the oxynium, right? Right. H2O forms what? OH, then plus what? H plus, yeah, this is negative, right? So now from this we go further to what? H3O, which is the hydronium oxide, right? So they form the oxonium, right? So that's basically that. Then we can say this is not the true formula. I want to give you the explanation here. We have what? H2O. This H2O is in liquid form. It dissolves to form what? The hydronium ion plus the hydroxide. This is what we call decomposition reaction, right? This is a liquid, this is aqueous, this is aqueous, right? According to the decomposition reaction, this is what is happening here. So now listen, this reaction is in equilibrium, meaning that it will go like this and it will go like this. Either way, if you add these two, they give you water. If you decompose water, it has to take you to this form. So now the equilibrium lies far to the left and a very small number of water molecule dissociates. So now the equilibrium constant for this is going to be what? The Kc is going to be the hydronium, yes, the hydronium, H3O plus, multiplied by the what? The oxide, the hydroxide, divided by your water, H2O, then all of this is squared. So now basically your Kw is just gonna be the product, right? Meaning it's going to be your hydronium, H3O ion, right, multiplied by the concentration of the OH. This is going to be the base, and this is going to be the acid. Now the concentration of the base and the concentration of an acid. So now we look at this. This is the ionic product of water, right? Ionic product of water. Ionic product of water, right? So now then we don't have a problem with that. This is basically Kw, right? So at least we have what? The 25 degrees Celsius of this. The 25 degrees Celsius is equivalent to your 298 Kelvin degree, right? Degree Kelvin. So now your ionization product or ionic product of water, Kw, is going to be what? 1 times 10 to the exponent negative 14. This is 1.00, or you can just take it to be 1, right? Now, from the equation, we can see that the concentration of the hydronium, right, or the H plus ion, equals to the concentration of the OH negative ion, the hydroxyl ion. So now that's basically that. Then we can simply say, if you have this like this, they are equal. Now this is equal to 1.0 times 10 to the exponent negative 7, right? That's that. So this line doesn't want to go, and it's fine. Let me try this other rubber here. Also it doesn't seem to budge, so it's fine. So that's basically that. It's concentration, so it's going to be mole per dm minus 3, right? Now that is that. A very small number of water molecule dissociates, and the concentration of the hydrogen ions and the whatnot ions at this temperature equals to 1 point. This is the point of neutralization, right? So that is what we can say about this, right? Now in simple terms, we can say H3O plus multiplied by the OH negative. This is going to give us what? If we say 1 times 10 to the negative 7, then 1 times 10 to the negative 7. The answer that we get from this is 1 by 10 to the negative 14. Then this is the solution. This is the answer. We still got our KW. So now let's go to pH. Now you can be able to calculate the pH solution, because the pH of a solution is the number that indicates the degree of the acidity or the basicity of that solution. In pure water, the concentration of hydrogen ions in it is equal and very small. It is awkward to work with very small numbers. To solve the problem, chemists use logarithmic scales to express such low ions concentration. Chemists use the pH, right? Remember, the pH of any substance is equal to negative log of what? The log of the hydronium ion, like this. So now all